thanks everyone for having me. Always delighted to talk about this kind of stuff. My name's Kevin. My talk for you today is called Game Development in 8 Bits, or the alternative title I went with as I was working through this was Stupid NES Tricks, which I'll talk about why that's the title. Before I really kind of jump in, the two main questions I think I need to answer are, first off, what is NES, if you're not familiar? We are going to be talking about the Nintendo Entertainment System. It is a product from Nintendo, shocking. A video game console that you would use in your home. You hook it up to a television set. It was first released in the United States in October 1985, and it was manufactured for about 10 years. During that period of time, the NES really kind of defined an entire generation of video games. It was at the point where if you were going to go play video games with your friends, your parents would be like, don't stay out there too long playing Nintendo, even if it wasn't an NES that you were playing. In those 10 years, about 700 licensed games came out for it that were produced by Nintendo in some form. The NES is actually a US revision of the previous Japan-only system, the Family Computer, or Famicom, came out 2 years earlier in 1983. The NES is really the same hardware as the Famicom, just in a different shell. It was redesigned to look less like a video game system or some kind of toy, and to look more like a VCR, something you could fit next to your hi-fi stereo system. Both of these systems, why they exist, the idea was to come up with a system where, as a baseline, it could play a reasonable home version of Nintendo's arcade hit Donkey Kong, which came out 2 years earlier. So in this case with Donkey Kong, not a huge amount of movement, but colorful backgrounds, decent amounts of animation, support for music. This was really kind of like what the designers of the system were aiming for. The previous kind of king of the video game systems was the Atari Video Computer System, or 2600. Came out in 1977, has this beautiful wood grain panel on it to match everything else in your 70s home. And it has these joysticks, which are very simple, just kind of like one button and a little joystick you can move around. And to give you an idea of how far the NES came from kind of this predecessor, the game the Atari 2600 was built to play was Combat. This game where you've got these very blocky tanks that move around slowly and shoot at each other, which Donkey Kong is kind of in its own category compared to this. The NES is built around an MOS Technologies 6502 CPU, running at 1.79 megahertz, blazing fast for the mid-1980s. It also uses a custom picture processing unit, which is kind of like the GPU of the system. It was designed and built by Ricoh, who nowadays are mostly known for making laser printers, but back then they were a chip fab as well. This chip allows the NES to display 256 by 240 pixels resolution to your TV, and it can display 64 different colors. That MOS Technologies 6502 was very popular. It's a processor that actually came out in 1975. It was used in a number of systems, including that Atari 2600. It also powered the Apple II series. It powered the Commodore 64. It is the chip that powers the Tamagotchi, if you know that. There's even an episode of Futurama where we find out that it is the chip that powers Bender. You can still buy these chips today. They're still manufactured. You can still work with them. The NES also features 2 kilobytes of system RAM. It has 2 kilobytes of video RAM. There's nothing really permanent about it. There's no permanent storage. There's no operating system. There's no real-time clock. You really kind of have to supply everything yourself. And how you supply those things is through these read-only cartridges. You get 32 kilobytes for your game code. You get 8 kilobytes for graphics data for your game. And that's it. So 40 kilobytes is what your entire game is going to fit into. We also need to talk about what 8-bit means, because it's going to come up a lot. So if you are not familiar, a bit is a binary digit. So it's either a 0 or a 1, an on or an off. There's 2 different states that it can represent. If you combine multiple bits together, you can represent more and more types of values. So 1 bit just has either a 1 or a 0, 2 possible values. But as you do more and more, you can represent bigger and bigger numbers. And when you hit 8 bits, it has a special name. We call it a byte. And that lets you represent 256 possible values. So numbers between 0 and 255, basically. An 8-bit system like the NES, the reason it has that name is because the 6502 CPU processes data 8 bits at a time. Or to put that another way, as far as the NES is concerned, basically everything in the universe is ultimately representable by a number between 0 and 255. That's how it thinks about everything. So that said, let's jump on in. First thing I'm going to talk about is drawing graphics. Very important thing for a video game system to do. As I mentioned before, your screen resolution is 256 by 240 pixels. And if we multiply that out, that means every screen of graphics, you need to draw 61,440 pixels. For reasons we'll get into, you can store about 4 pixels in a byte. That means that you need about 15 kilobytes to store a single screen of graphics if you're doing this pixel by pixel. And that's a real problem because the system only has 2 kilobytes of video RAM. You wouldn't be able to fit a complete screen in memory to draw it if you were doing this way. So how do you draw a screen of graphics when all you've got is 2 kilobytes? For the NES, the answer is you sort of get abstract. And a lot of game systems of this time period used a similar approach. They don't draw with pixels because they can't. There's not enough memory to do that. So instead, they draw with tiles. Tiles for the NES are 8 pixels by 8 pixels square. Those tiles live in what's called a pattern table. So the 8 kilobytes of graphics data that your cartridge has access to are literally just these 2 pattern tables. Each one has 256 tiles in it. There's that number again. And you basically get kind of 1 pattern table for sort of foreground objects and 1 pattern table for sort of background objects. So these are the 2 pattern tables from Super Mario Brothers for the NES. Literally everything that Super Mario Brothers will ever draw to the screen in that game is in one of these 2 pattern tables. We also work, as I kind of introduced, you use this concept of layers. So here's an example screen from Super Mario Brothers. When the NES goes to draw this, the way that this is actually coded, it's really 2 layers that are superimposed on top of each other. There is a background layer, which is the background, things that do not really have to move around a ton. And then we have this sprite layer, which is things that are going to move around a lot, things that need to be positioned to individual pixels on the screen. So I'm going to talk about backgrounds first. Backgrounds for the NES are a 32 by 30 grid of tiles. And you're literally just slotting tiles into those spaces in the grid. So when you multiply those 2 numbers together, there's 960 tiles in a screen. And you only need 1 byte for every tile, because literally all you're doing is saying, for this position in the grid, here is the tile between 0 and 255 that belongs there. So as a result, you can store a whole screen of backgrounds in 960 bytes, which is a massive improvement over the 15K that you would need to do it pixel by pixel. Now for sprites, they work a little bit differently. You get 256 bytes of sprite RAM, which lives in its own kind of separate place on the system. And it takes you 4 bytes to store every sprite. You need to know the tile number, just like with those background things. You need to store the X and Y position of where you want it drawn on the screen. And there's an extra byte which lets you decide sort of which palette it gets drawn with. You can do different kinds of colors this way. And some optional things like sprites can be flipped, basically horizontally or vertically. So as a result of that, you can draw 64 sprites at a time on screen, which sounds like a lot. It's actually smaller than it sounds because most of the things that get drawn are not just a single sprite. 8 by 8 pixels is very small. So Small Mario here from Super Mario Brothers is actually 4 sprites that are working together as this 16 by 16 thing. So In theory, you could have 64 objects. In practice, it's going to be much smaller than that. That all works great for one screen. We haven't talked about how you do things that are bigger than that. Donkey Kong, everything takes place on a single screen that never scrolls, so it's really easy. But other games are a lot bigger. Super Mario Brothers, for example. This is World 1-1, very first stage of that game. It is 14 screens in length. So if we were going to store this in the simplest possible way, we've got 14 screens of graphics. It takes us 960 bytes for each and every screen. That means you need about 13 kilobytes to store all this level data. And that's just for the very first stage. So here is that World 1-1 again. And if we're going to store all the level data for Super Mario Brothers, we also need to worry about 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4. And then we have to do that 4 more times because Super Mario Brothers has 32 stages, and each stage is minimum 10 screens long. So how do you store all of that in 32 kilobytes and still have space left over to write all the logic of how the game actually works? You get abstract again. Not really that shocking. One way to do that is to use these kind of repeated meta objects. So here is an example of a background from Mega Man 2. It's got a lot going on, but in reality, everything on this screen is just one of the 3 blocks on the right side, repeated in different patterns and shapes. So one way to really cut down on your usage is to have these sort of larger blocks that can repeat within a level and still create something that looks interesting. A lot of games also use some kind of basic compression. For the NES, which is not very strong at math, that's usually something like run length encoding. So instead of storing these 96 brick tiles at the bottom of the screen, the code can literally just be, here is the tile, now go repeat it 32 times. And then they don't have to store 32 bytes for it. They can just store a single byte and how many times it repeats. For Super Mario Brothers, it's interesting. It gets kind of even a layer beyond these sort of meta objects or meta tiles. Super Mario Brothers uses what people who studied the code for it like to call set decoration. So it's got these 3 screens of background that repeat endlessly in the back of a level. The main thing to note here is there's a pattern to the hills and bushes on the ground, and there's a pattern to the clouds up in the sky. And once you know about this pattern, you spot it everywhere. So here are 6 screens from World 1-1. You can see that pattern of clouds repeating. You can see that pattern of hills and bushes repeating. And what that allows the game to do is, in order to store this level data, all they need to store are the parts that are different from that set decoration. And they have kind of a default that's always running behind them. So as a result of this, Super Mario Brothers is able to store World 1-1 in 101 bytes. There's a header and a footer that kind of tell the game code where the level data starts and ends. And then in the middle, there are these pairs of bytes. And each pair is a location on screen and what to draw there. So the first one, where the first byte is 07, is saying go to column 0, go to row 7, and then draw whatever 81 tells you to draw, which in this case is a question mark block that has a coin in it. Or 47, go to column 4, row 7, and then draw whatever byte 24 tells you to draw, which in this case is a row of 4 bricks. So it's a very, very compact format, and that's what allows Super Mario Brothers to fit this massive amount of level data into a very small area. Let's talk a little bit about physics. To kind of go back, I mentioned before the Atari 2600. Probably the best looking, most technically impressive Atari 2600 game is Pitfall, in my opinion. It's a game that came out in 1982, so 3 years before the NES, the year after Donkey Kong. It's got a lot going on for an Atari 2600 game, but the hero character here runs at a constant speed. He has a jump, but it feels sort of weightless. It doesn't really feel like a real thing. When you compare that to Super Mario Brothers, Mario has momentum. He starts slow, he accelerates over time. When he comes to a stop, if you just like suddenly change directions, he kind of skids to a stop a little bit before he turns around. It has a very different feel from how Pitfall works. So how do you do this on the NES? The 6502 knows how to do 4 math operations. It can add, it can subtract, and it can do bit shifts left and right, which are basically multiplying and dividing by 2. And that's all it knows how to do. If you want to do something that's not part of this set, if you want to multiply by 3, your code basically needs to write a function that does multiplication by 3 using these 4 functions. So how do you handle physics like the way Mario feels like he has physics when really all you've got is addition and subtraction? A number of approaches. What a lot of games end up using is basically faking it. They use what are called fixed point fractions. So you're probably familiar with floating point, where you can have sort of arbitrary precision of how many digits come to the right of the decimal point. Fixed point in this case is, they call it 8.8 for the NES. You've got 8 bits on the left of the decimal point, and you've got 8 bits on the right of the decimal point. So you can express fractions of 1/256th of something. A lot of games just track positions using 2 bytes instead of 1. So the first byte is where on screen something actually is, an actual number from 0 to 255. And the second byte is like the fractional part of how many pixels they're moving. In the case of Super Mario Brothers, it really only cares about multiples of 16. It doesn't even use the full range of what's available. But what this allows you to do is you can express things like the speed of something moving in 1/16 of a pixel. And when you do something like that at 60 frames a second, which is what the NES is doing, that allows you to get this very kind of fine-grained feeling of acceleration or changes in velocity without having to do complicated math. One more thing before I leave physics is to talk about collision detection. You might be getting sick of Super Mario Brothers by this point, so instead I'm going to talk about Contra. Contra is a game that came out in 1988, made by Konami, very popular in arcades, and had a really good NES port. It has this box art, which is a total ripoff of basically Predator and Alien combined. It allows for 2-player simultaneous play as well, which was really interesting for the time. Contra also moves very fast. There's a lot of things coming in and off the screen. Enemies are firing at the player is firing at enemies. There's lots of things flying around. And to make collision detection even more interesting in this case, things just have a lot of different sizes and shapes. So the player character can be in any of these positions that are on the left side of the slide. Standing up tall, lying down flat, jumping in the air, tucked into like a little ball shape. And the enemies come in a wide variety of sizes and shapes as well. So if you're going to do collision detection, usually the way that people do this in a modern sense is you've got a rectangle around the player, you've got a rectangle around the enemy, and you need to check if these 2 rectangles overlap in some way, which requires you doing math relatively fast. And on Contra's case, there's a lot of collision detection to do. So here are the 2 players playing simultaneously. They have managed to collectively put 11 bullets onto the screen at once, which are all of those white arrows. And each of those 11 bullets needs to be checked against 4 possible enemies that can be hit, which are marked with those gold arrows. We also need to check those gold arrow items against the 2 players individually to find out if one of them got hit by something. And we need to do this 60 times a second, which means we've got about 16 milliseconds to find out whether or not these collisions happened every single time. So obviously that's difficult when all you have to work with is addition, subtraction, and shifting left and right. So how do you make that work? The developers of Contra had a very interesting solution to this. Instead of doing two rectangles and trying to find out if they overlap, they were like, let's simplify this as much as we can. They came up with a system where they check a point against the rectangle. So you can pretty easily say, is this point inside the rectangle or not? And interestingly, they decided the player is always going to be the point. So in this slide, you can see there are these green dots that have a green circle around them. And that is the point that represents the player that is being used for collision detection. There's also kind of this white plus sign shaped thing. That is an enemy bullet that's going to be checked. Did it hit the player to kill them? The rectangle in this case, around the rectangle that's used for collision detection with that bullet is representing the shape of the player at the time that the collision detection check is happening. So for each enemy, you don't care about how big the enemy is. All you really care about is at what point would that rectangle overlap with the player and count as a hit. So each enemy in the game basically has these three rectangles, which represent the three possible ways you're going to get a collision. It cuts down the amount of data that needs to be stored, and it makes the mathematical checks a lot faster. So speaking about math, a good time to talk about random numbers. Another thing which many video games need, not as many as you might expect, especially in the NES era, but still an important thing for games to be able to do, especially puzzle games. So Tetris, early kind of breakout hit for the NES. Tetris lives or dies by its random numbers. It needs random numbers to figure out what piece is going to come next, and they can't come in a sequence or else the game becomes predictable. RPGs, Final Fantasy, a big early example, it needs random numbers so that as you're walking through the game and doing stuff, it can know, do you get into an encounter with some enemies? If you do, what's there? Which characters do those enemies try to hit? Do they actually succeed in hitting? All kinds of stuff like that. So doing this in kind of like a modern language, if you were going to do this in JavaScript, you'd use something like this to get a random number between 0 and 255, and you'd be good. The problem is the NES doesn't have a random number generator. There's no system-level source of randomness that you can just tap into. So every game needs to write its own method for coming up with random numbers. So how do you do that? I'm going to show you three approaches. They are ordered from kind of like the most to least complex. Earlier, I called these the most to least stupid. I've gotten some pushback on that, so I'm very curious to see what people think about these. The first one I'm going to talk about is Tetris. Tetris's solution is to do it with math. They use a construct called a 16-bit Fibonacci linear feedback shift register. Which is quite a mouthful, but it's basically you take this 16-bit thing, you do some XOR operations with individual bits within it, and you read the rightmost byte of it as your random number. It does a pretty good job. Final Fantasy takes a different approach. If you've played this game before, there's a moment fairly early on where your characters cross a bridge, and suddenly you get this big cutscene where there's a text box that tells you about what's going on. And it pauses at this point, and you see this phrase, programmed by Nasser, which as a kid, I had no idea what this meant. It turns out Nasser is actually one person. It's Nasser Gebeli. He grew up in Iran. He emigrated to the US in the 70s. He eventually went to Japan to work for a then totally unknown company called Square. And he is the one person who wrote all of the code for Final Fantasy. He also wrote pretty much all the code for Secret of Mana later in the Super NES era. He was a very busy guy because no one else was there to help him write the code. So he needed to come up with a super simple way of getting random numbers for this game that heavily depends on random numbers. And his approach was to use a lookup table. So buried in the code of Final Fantasy is this table of 256 pre-computed random numbers that have just been written in hard-coded. And Final Fantasy just uses a pointer into this table. And every time it needs a random number, it just increments the pointer by 1 and gets the next entry out of the table. So all of the random numbers come in an extremely predictable sequence, but it's very hard for you as a player at home to know what's coming next. It's very hard for you to even know what numbers were selected to try to write it down and figure it out. And so for that reason, it actually works really well for what Final Fantasy needs. The third approach is actually from Contra. Contra needs random numbers because there are these enemies that randomly come from the left and right sides of the screen, and Contra needs to know when and where to actually make them pop up. Contra has the most interesting solution of all. It basically keeps 1 byte in memory, and when the game is not busy doing something else, like collision detection, it just basically adds a number to that byte of memory over and over and over again until it needs to go do something else. And wherever it left off is your random number. Basically, the idea is if you're not busy, like add 7 as fast as you can. And once you go beyond 255, it's just going to overflow back to 0. And just do that over and over and over again. And based on like how busy things are going on screen, you'll get different amounts of randomness, I guess, because it'll take different amounts of time before it's ready to start the next frame. So enough on those. I'm going to talk about saving. Something that was really kind of new for the NES. So when these were primarily arcade games, the idea was that you were going to play them for a relatively short amount of time. If you could go to a Donkey Kong machine in the arcade and put in your quarter, and you could play for 5 solid minutes, you were halfway decent at Donkey Kong. That changes when you move into the home setting, because now people are putting down $50 or $60 to buy a brand new game, and they want to get their money's worth out of this. They don't want something that only lasts for 5 or 10 or 20 minutes. They want something that they're going to be able to play for hours to get their money's worth out of it. And like a game like Final Fantasy, which is super long, it's like a 30-hour game to play through from start to finish. People are not going to sit there with their NES turned on for 30 hours to just get through this game. They need the ability to save and come back later. So how do you do that when your cartridges are read-only? There's no way for you to write data into the cartridge to save for later after the power gets turned off. Different games take different approaches. Mega Man 2 uses this kind of password system. So it gives you this grid. Every time you get to sort of a milestone in the game, it'll present you the grid, which you can then write down in a notebook somewhere and put it back in when you come back to the game to pick up where you left off. The way this works internally is very simple. It's just there are 8 bosses in the game. For each boss, is it alive or is it not alive anymore? Did you beat it? And also, how many of these things called E-tanks, which are one-time use only, how many of them have you picked up over the course of your playthrough? That gets you all of this. Punch-Out, a Nintendo-made game, also has a password system. It uses this 10-digit number, which it will give you after every certain milestone in the game. You put in that password, and you can pick up basically right where you left off. Nintendo did not want people to reverse engineer how this works. So the Punch-Out password system is fiendishly complicated, where it's taking what are basically win, loss, and KO counts and scrambling them together in a wide variety of ways to come up with this final thing. Very difficult for someone to come in and sort of figure out how the password system works. Lastly, Dragon Quest II. This is an RPG, came out for the Famicom in Japan. Eventually, it was ported to the US for the NES. When Dragon Quest II came out in Japan, it used passwords. This is a game that, again, is like 30 to 40 hours in length. It has 3 different characters that it needs to track stats for all of them. So the password that you were given is basically like a poem. You need to record this thing into a notebook or something like that. And then you need to use this absolutely massive keyboard that shows up on screen, which is incredibly frustrating to use. So as games got bigger and bigger, more and more complicated, this idea of using passwords became less and less palatable to consumers and to Nintendo itself. So Nintendo in Japan said, let's come up with an alternate way of doing this. And the system that Nintendo came up with was the Famicom disk system. So they said, we're just not going to use cartridges anymore whatsoever. Instead, people will buy this big disk drive that fits under their Famicom and that plugs into it with this adapter. And you'll start buying all your games on disks instead. They're kind of like a floppy disk, sort of. They don't have that metal shutter that keeps them closed and keeps dust out of them. One other thing to notice is that they have the word Nintendo kind of stamped into the plastic at the bottom of the disc. This was a form of copy protection because Nintendo was paranoid that people were going to steal their games. So the Nintendo at the bottom, the I and one of the N's are indented at a very specific way. And inside the disk drive, there is a metal plate that needs to fit into those stamps in just the right way. And if the plate doesn't fit, the disk drive will just refuse to play the game. It'll assume that it's pirated or somehow not real. The problem for Nintendo is that they chose to use as a format what was called the Mitsumi Quick Disk, which in Japan, at least in 1986, was the kind of disk you could just go to a store and buy a whole box of. It was 2.8 inches in size. Here it is with the standard 3.5-inch floppy save icon for size reference. So you could buy these in bulk quantities, and it did not take long for players to figure out that with just a little bit of ingenuity, you could buy these quick disks from the store and turn them into things that the Famicom disk system would actually read and accept. The situation got so bad that within a year of the Famicom disk system coming out, manufacturers were actually creating disks that had this plastic thing stamped into it already because they knew what you were trying to do, and they knew there was a market for it, and they started providing it. Nintendo obviously was not happy about this. The Famicom disk system was only on the market for about 1 year before they pulled the plug on it, which took them back to the drawing board. You still need a way to save your game data, but you can't use a disk like this because people can put it in their computer and just copy your games. So how do you make this sort of writable game media and make it so that users can't copy the actual game data itself? The solution they came up with was you just put more stuff inside the cartridge. So they started coming out with a series of what were called memory mapper chips, or MMCs. So this particular game uses the MMC1, which is kind of like the first popular one that came out. And what that MMC1 allows you to do is you could slap a tiny little coin battery onto the cartridge, and you could put an extra chip full of RAM. So that when you write some data into the RAM and you turn off the NES and you pull it out, that little battery keeps the RAM alive and saves whatever data you have. Which leads to its own problem. You start seeing these things in like manuals for games and sometimes even on the screen itself, telling you need to hold in the reset button when you turn off the power. Very important. If you don't do this, it's going to destroy your save games. So what is going on with this? When you turn off any kind of computer like the NES, it doesn't go from on to off just immediately. You turn off the power, and very, very quickly, it loses all that electrical charge that it has that's powering it. But there's a brief period of time there where it's still running, and it now has less electricity, so it's kind of erratic, where like some things work and some things don't. So it is rare, but it is possible that as the NES is turning itself off, that processor could do something unexpected and write data into that RAM chip on the cartridge and just blow away everything you have, or at least corrupt it. Holding in that reset button kind of locks the CPU into a very tight loop where it's not allowed to actually run any instructions, which prevents this from happening. So great, you have a way to avoid it, but you don't know that your player has actually done that. So when your game starts up, if you're going to load a saved game, how do you know that the save data is actually good and that it's not just corrupted garbage? Dragon Quest, which was released in the US as Dragon Warrior, which used this kind of system instead of a password, it just writes your save multiple times. It's got something like 8 kilobytes of RAM to work with, so it just stores like 8 copies of your save data at differently spaced positions in that RAM. And it writes a little checksum CRC code at the end of each save. So when it goes to load up your game, it checks the first save, it compares it with the checksum, and if it's good, it just loads that and you're done. If somehow you didn't hold that reset button and something got corrupted with that first save, it just goes to the next one in the list and checks that, and goes to the next one in the list and checks that. And eventually, if all the saves are bad, then it just doesn't give you the ability to load a save. So that's kind of the core of everything. What is the point of all of this? Why have I been telling you all of this weird 80s trivia for the last 30 to 35 minutes? There are a number of things you can learn from this, but at least for me personally, the thing that I have really learned from doing all this research and finding out about all these old games is there's a sense of value in embracing a stupid approach to something. Most of these NES games are not doing things the way you would nowadays because they just didn't have the processing power for it, but they're still really good. Like that random number generator in Final Fantasy, which is entirely deterministic and has like no variation whatsoever, is still really entertaining to play with. It still works really well for what the game was trying to do. So what I mean by this is, don't be afraid to do something that is a relatively dumb approach to something if it works. If it gets you what you want, your end user is not going to know if this is the most elegant possible solution or if it's something kind of hacky that you threw together. This advice does not apply if you are writing software that controls airplanes, automobiles, nuclear power plants, those kinds of things. I want to live. Do not follow this pattern if that's kind of where you're going. But in general, like, don't feel bad to write code that is kind of ugly. There's nothing wrong with it if it gets you the result that you want. So that's kind of the end of the main presentation. I've got a few other things I'd like to talk about since I've got some time. One of those is that people keep making NES games to this day. To give you some recent examples, one homebrew developer, Brad Smith, he came out with a game in 2018 called Lizard. It's an NES game. You can buy it on a physical cartridge. You can also buy it on Steam. It's like the NES ROM wrapped into an emulator and sold as a single package. There's also this game called Micro Mages, which came out a couple of years ago. This is really impressive because it allows for 4-player simultaneous play. So if you have an NES and you've got the right kind of hookups for it, you can connect 4 controllers and you can all play at the same time with this game. Here are a variety of homebrew developers. These are all people who are very active making stuff for the NES to this day. There's this one list here of homebrew games. There's all kinds of other stuff too. If this is something you really want to learn more about, one thing I would definitely point you to is this book from 2015. It's called I Am Error. It was like a PhD thesis. It's published by MIT Press. It's part of a series called Platform Studies. All the books in it are great. This was kind of the book that first got me into seriously exploring how the NES works and how to write code for it. You can go to the NES Dev Wiki. This is kind of like the homebrew community where they collect all of the things that they have learned about how the NES works. Fantastic reference. It would be virtually impossible to do this kind of stuff without it. I've also been working on a Creative Commons licensed tutorial series / book thing, like Blake mentioned. It's called Famicom Party. It's available at this website. I'm planning to get the next chapter up within the next couple of weeks. And once I do that, I think everything will be here that you would need to make like an actual full game. The goal is to sort of walk you through how to write assembly code for the NES, assuming that the only thing you know is how to write code for some other modern programming language, like a JavaScript or a Ruby. And that's it. Thank you all very much. Here's my email address if you'd like to get in touch. I'm very happy to get email from people.